Welcome to The Explainer. I am absolutely thrilled you're here with us today. On the surface, what we're looking at seems like, well, a child's backyard toy. But underneath, it holds the exact same complex engineering principles that actually take humanity to the stars. Today, we're exploring the surprisingly profound physics of water rockets. We are literally going to transform a simple plastic soda bottle into a masterclass in aerospace engineering, aerodynamics, and fluid mechanics. So get ready, because this is going to be a really fun ride. To really set the stage for this, let's look at a staggering number, 8.8 million. That is the amount of thrust, measured in pounds, generated by NASA's Space Launch System, or the SLS. To put that into perspective for you, that's the equivalent power of about 880 jet engines firing all at the exact same time. It's just the sheer brute force required to tear a massive payload away from Earth's gravity. Okay, let's dive into this, because here is the wild part. The exact same physical laws governing that massive Earth-shaking SLS launch apply directly to a humble, empty 2-liter plastic bottle sitting on your lawn. Now, obviously the scale is vastly different, but the math, the forces, and the overall challenge of balancing mass and energy, they're practically identical. So here is our roadmap for today's explainer. We're going to cover 1. Newton's laws in action, 2. Air energy versus water mass, 3. The surprising physics of thrust, 4. Finding the optimal ratio, and finally, 5. Safe launch protocols. All right, kicking things off with Section 1, Newton's laws in action, the very foundation of flight. If you look closely at how the forces are mapped out here, notice that intense downward spray. That right there is Newton's third law happening in real time. The law states that for every action, there's an equal but opposite reaction. The pressurized air inside our bottle forces the water out of the nozzle at the bottom. That violent downward expulsion of water, that's our action. In response, an equal and opposite force pushes the bottle upward. That upward reaction is our thrust, and it literally has to overcome both the downward pull of the rocket's weight and the drag of air friction. Which naturally brings us to Newton's second law. Force equals mass times acceleration. Or, to summarize it super simply, a bigger force causes a bigger acceleration. If you try to launch a bottle with only pressurized air, well, it won't go very far. Air has very little mass, so pushing it out doesn't create a strong action force. But water? Water is heavy. Throwing that heavy mass of water downward requires a lot of force, which in turn generates a massive upward reaction force, accelerating your rocket high into the sky. Moving right along to Section 2, air energy versus water mass. This is the core conflict of our design. So, if water is what gives us that massive push, I gotta pose a question to you. Why not just fill the entire plastic bottle with water? Pump it up and let it rip, right? Take a second and just think about what would actually happen. Well, the crucial point here is understanding the completely distinct jobs of our two ingredients. Water is practically incompressible, meaning it literally cannot store energy when you pressurize it. Air, on the other hand, is highly compressible. It acts just like a tightly coiled spring, storing massive amounts of energy when you pump it up. But as we mentioned, air is way too light to provide a good kick. So the air provides the stored energy, and the water provides the heavy reactive mass. And because they have to share the exact same physical volume inside the bottle, you're forced to trade one for the other. Too much water, you've got a heavy rocket with zero energy to push it. Too much air, lots of energy, but absolutely nothing heavy to throw. That brings us to Section 3, the surprising physics of thrust. Prepare for a really cool math twist. Okay, here's a totally counterintuitive thought experiment for you. Imagine you have a water rocket and a Stender potato gun. Both have the exact same nozzle or barrel area, and both are pressurized to the exact same PSI. Which one produces a more powerful thrust force? The answer is actually the water rocket, and not just by a little bit, but by a factor of exactly 2. The thrust of a solid projectile like a potato gun is just pressure times area. But according to Bernoulli's equation for fluid dynamics, the thrust of a water rocket is 2 times pressure times area. And this brilliantly illustrates the difference between solid mass and fluid mass. Take a moment to really process this. A solid potato chunk starts at 0 velocity and has to accelerate down the barrel, so its average speed is only half of its final exit speed. But a stream of water in our rocket seemingly bypasses that active acceleration entirely. It instantly shoots out of the nozzle at its maximum constant exit velocity. This means the water provides a much stronger force for a shorter amount of time, giving you exactly double the mathematical thrust of a solid projectile at the exact same pressure. How cool is that? Let's jump into Section 4, finding the optimal ratio through iterative engineering. Before you ever head outside to the launch pad, the absolute most efficient method is iterative engineering using digital simulators. You plug in your rocket's total volume, the dry weight, and your nozzle diameter. A really great starting point is filling about 1/3 of the bottle with water. You run the simulation, you note the predicted peak altitude, which we call apogee, and then you incrementally adjust the water volume up or down. You just keep running the math over and over until you find that absolute sweet spot for peak performance. And looking at the data from thousands of simulations, a really clear pattern emerges here. For smaller rockets with narrow nozzles, your optimal fill might be as low as 20 to 25%. For larger, heavier rockets with wide nozzles, you generally want more water, peaking closer to 33 or 35%. But keep in mind, the mathematical optimum on a computer isn't always the reality of outdoor flying. Because here is a brilliant practical tip. Using slightly less water than the math dictates is actually often better. Why? Well, water is incredibly heavy. Having heavy water lingering in the tail of your rocket shifts the center of gravity backwards, making it highly unstable right off the launch pad. By using slightly less water, the rocket expels its mass faster and accelerates quicker, which actually allows the fins to catch the wind and stabilize the flight path much, much sooner. All right, finally, Section 5, Safe Launch Protocols. Time to prepare for liftoff. Now listen, these are non-negotiable safety rules drawn straight from NASA educator constraints. First, you need a wide open grassy field, at least 30 meters wide. Second, pressure limits. While you might be tempted to push for more thrust, never pump a plastic bottle past 90 psi, absolute maximum. Honestly, 40 to 50 psi is plenty for fantastic flights. Always wear eye protection. Keep in mind that repeated pressurization weakens plastic over time, so you absolutely must retire and replace your rocket bottles after 10 to 15 launches to prevent an explosion right there on the pad. And it goes without saying, never ever lean over a pressurized rocket. So let's bring this whole thing full circle. 1,100 miles. That is the apogee of NASA's massive space launch system. But the journey to 1,100 miles and the fundamental understanding of exactly how to get there starts right here. It starts with an empty soda bottle, a bicycle pump, and a profound hands-on appreciation for Newton's laws of motion. Before we wrap up, I want to leave you with one final, kind of provocative thought experiment to really test what we've learned. If adding mass gives us more thrust, what if we replace the water with a denser, heavier liquid, like saltwater brine? It turns out your rocket would actually fly lower. Crazy, right? Why? Because while the heavier liquid does generate more thrust when it's expelled, the rocket also has to physically accelerate that heavier mass while it's still sitting inside the bottle during those crucial initial moments of liftoff. It is a beautiful, deeply complex balancing act. I really encourage you to take these principles, build your own safe launch pad, and see these physics in action for yourself. Thanks so much for joining me on The Explainer.